Hello everyone. Today I'm going to talk about our work in empirical study of the effect of source level loop transformations on compiler stability. So before I start talking about compiler stability, let's imagine a perfect compiler. So a hypothetical perfect compiler would produce the highest performing target code from a piece of source code. This would imply that the perfect compiler would produce target code with the same performance for semantically equivalent variations of the source code. Then we can define the compiler stability as a compiler's ability to generate target code with stable performance from structurally different but semantically equivalent source code. Let's take a look at these two examples here. So these two pieces of code are the interchanged version of each other. So if we have a stable compiler, it will recognize one of these versions has a subpar memory access pattern and interchange it to the better version. So they will produce the same target code, or at least the same performance. So the importance of the compiler stability is that with a stable compiler, the programmers can focus on code readability and algorithm selection without worrying about performance. Also, most work is done in loops in compute-intensive applications, and for loops or similar constructs is usually present in modern programming languages, and its analysis and transformations are well understood. That's why in our work, we mainly focus on the compiler stability on C languages for loops. In addition, vectorization support is common in modern processors and can have a significant impact on performance and stability. Code structure can also enable or disable vectorization or affect its effectiveness. For example, if we have a piece of code that has non-unit stride access, we usually need to apply gather-scatter overhead operations to enable vectorization. Also, the accuracy of the profitability model of the vectorization is crucial because vectorization is not always profitable. Therefore, in our work, we also assessed the effectiveness of compilers' auto-vectorizers. Although the compiler community is aware of the existence of such instability, its magnitude is never measured. So we present the first quantitative study on compiler stability. And our methodology also allows us to estimate the lower bound of a compiler's performance headroom. Therefore, we measured the stability and performance headroom of 3 popular C compilers against for loops. Now let me talk about our methodology. Our methodology consists of 4 basic steps. The first step is to build a collection of loop nests from benchmarks and libraries. Then we generate semantically equivalent mutations from the extracted loop nests. After that, we compile the original loop nest and their mutations with different vectorization settings. And finally, we measure the performance variation between the mutations and the original loop nests in order to assess the stability. In the first step, we programmatically identify and extracted 4 loop nests from the AST of the original programs. We also identify the input, which are the read-only and write-after-read variables, and the output, which are the write-only and read-after-write variables from the loop nests. With this information, we were able to instrument and then execute the original program to capture the input data to the loop nests. Finally, we encapsulate each loop nest into a standalone codelet that executes the loop nest with the captured data. The codelet also records the execution time and read a couple of hardware performance counters for detailed analysis later. The second step is to generate loop mutations. In this step, we programmatically apply sequences of loop transformations to the loop nest in each codelet. These sequences consist of 5 basic transformations: loop interchange, loop tiling, loop unrolling, unroll and jam, and loop distribution. Before applying any of these transformations, we use dependence analysis to guarantee the semantic equivalence of the resulting loop. We create codelets that contains the transformed loop nest, and we call these codelets mutations. So any of the transformation sequence that we apply is a subsequence of two predefined transformation sequences. They are interchange followed by tiling, followed by distribution, and followed by enrolling. And also interchange followed by enroll and gem, followed by distribution, and then followed by enrolling. For each basic transformation, we also apply it with a limit set of different parameters such as tile size and enroll factors. With these two steps, we were able to extract over 1,100 loop nests that execute for over 1,000 processor cycles from 13 benchmark suites and several libraries. And from these extracted loop nests, we were able to generate over 65,000 mutations, which means that on average, there are over 60 mutations generated for each loop nest. The extracted loop nests, along with their mutations and the profiling results, are publicly accessible on vectorization.computer, and it's provided as a repository and published in our ISWC paper last year. So in this work, we evaluated recent versions of Intel C compilers, GNU C compilers, and LLVM-C front-end. And when we assess the stability against loop transformations, we compile the code with the reference compilation, which is -03 with the default vectorization profitability model and several additional flags that facilitates vectorization. When we assess the auto-vectorizers, we applied several other compilation settings with the vectorization profitability model disabled when possible. These settings are to generate scalar code only and allow vector code but with SSE extension only, and allow vector code with SSE and AVX, and finally allow vector code with up to AVX2 extension. The performance is profiled on an Intel Xeon CPU of the Haswell generation. Now let me talk about our results. First, we propose several metrics to quantify compiler stability. The first metric is called Intra compiler stability score. It measures the average performance variation of the code generated by a compiler from semantically equivalent mutations. It is calculated as the average coefficient of variation of the execution time of each loop nest and its mutations compiled by a given compiler. By definition, a higher score would indicate greater instability, and a perfect compiler would score 0. Our result shows that ICC among the three compilers is the least stable, while CLAN is the most stable. Here we have two plots that illustrate the results. On the left is the stability score of individual loops compiled by the three compilers. And as you can see, in general, the curve for ICC is above the curve for GCC and then above the curve for CLAN, which means that on average, ICC is less stable. And the plot on the right is the performance difference between the best mutation and the worst mutation of a given loop. You can see that for the performance difference in the extreme cases, it also correlates to the stability score that we have. And we can see that for about 10% of the loop that we tested, the performance difference can be 4x or higher. The second set of metrics is called inter-compiler stability. It measures the average performance difference among the code generated by different compilers. And the first score is the pre-transformation inter-compiler stability score. So it assesses the intercompiler stability from the same loop structure and is calculated as the average coefficient of variation of the execution time of each original loop nest compiled by different compilers. We also have a post-transformation intercompiler stability score. It measures the average performance difference among the code generated by different compilers for better performing variants with the same loop semantics. And it is calculated as the average coefficient of variation of the execution time among compilers for its fastest mutations, which may vary across compilers. For example, for a given loop, ICC may prefer the loop to be unrolled, but while GCC may prefer it to be distributed. So we found that before applying any transformation, the stability score is at a higher value of 1.39. And after applying transformation, the stability score becomes lower at 0.96. This indicates that first, initially lower performing compilers may benefit more from well-structured source code than initially higher performing compilers do. And also source-to-source level transformations may narrow the performance gap between compilers. And we have an intuition here that compilers' performance may converge to a local minimum with the help of better code structure. And we call it the convergence effect. For performance headroom, we estimated the lower bound of the average performance headroom with the following formula. So in the formula, for a given loop, if there exists mutations that's faster than the baseline, we use the performance difference between the fastest mutation and the baseline as the headroom. Otherwise, we estimate the headroom to be 0%. With this method, we found that with source-to-source transformation only, the headrooms are from 30.8% to 20.9%, depending on different compilers. And with both transformations and best vectorization settings, the headroom rises to 18.1% to 26.4% accordingly. In general, we found that CLAN has the highest headroom and ICC has the lowest headroom among the three compilers. Because ICC on average performs better on the baseline loop nests, these results also confirm the hypothesis of the convergence effect. Now let me discuss a bit further on our results. So we investigated how individual basic transformations affect performance by first analyzing the correlation between the performance matrix that we read from hardware performance counters and the execution time before and after applying each transformation. We also studied selected cases which different transformations impact performance significantly. So please refer to our paper for details of these two studies. From these studies, we were able to come up with several heuristics. For transformations, we found that sequences of transformations provide limited additional benefits over single transformations, which means that just some simple changes to the loop structure can already provide great performance benefit. And also, we found that different compilers may prefer different mutations of a loop nest. This suggests that it's hard for a programmer to write a loop structure that can be optimized well by all the compilers. For interchange, we found that the compilers should interchange more loops with obviously subpar access patterns, which surprisingly they are not doing so currently. For unrolling, we found that it will be much more beneficial if the compilers unroll more loops with more loop bodies. We also found that loop unrolling can jeopardize strip mining-based vectorization, but help basic block vectorization. This implies that it's hard for programmers to predict the effect of unrolling when both vectorization techniques are implemented in a compiler. For vectorization, we found that source-to-source transformation can affect the effectiveness of auto-vectorizations. Depending on the compiler, we found that 36 to 38% of the loop nests that are not vectorized originally can be vectorized and sped up by at least 15% after applying one of our transformations. This suggests that programmers still need to understand how vectorization works and structure their code accordingly in order to make good use of auto-vectorization. We also found that code with older vector extension can outperform code with newer vector extensions. Most importantly, we found that the accuracy of the profitability model is crucial for vectorization, because inefficient vectorization can produce code that is slower than the scalar version. And we found that the missed prediction rate of their vectorization model is between 8% to 9%. In conclusion, we believe a hypothetical perfect compiler must be stable, and practical compilers should strive to approach it. A naive compiler is innately unstable because it does not apply any optimization to differently structured code. However, a sophisticated compiler can also be unstable too, due to its brittle optimization passes. We find that it's hard for programmers to write loop structure that always perform well when compiled by different compilers. And we confirmed that the studied compilers are far from being stable. Finally, we proposed a set of stability scores for the community to track the progress of compiler stability in the future. And we hope the community can use our framework and metrics to develop more stable compilers. And this concludes my talk. Thank you very much.
Yeah, hi. JP here from TU Darmstadt. Interesting things you said. So you tested a lot of different loops and ways to write those loops. Were you also able to identify certain patterns that are preferred by compilers, such that you can actually tell developers like how you should write the loops to benefit most if you're using a specific compiler?
In this study, we haven't done so, but we do have all the data that we can later work on to extract these informations. Thanks.
So I actually have two questions, but I'm going to start with one and then maybe pass the mic around. So on your first discussion slide, when you said that sequences of transformations don't seem to help over like single transformations.
Yes.
Do you have any intuition as to why that might be, or what's going on, or what's going on?
So when we apply more transformations to a loop nest, the structure of the loop nest tend to become more complicated. For example, for certain transformation such as unrolling, we may need to produce a residual loop for the enrolled version, and if we apply additional transformation to it, it may just make the structure more complicated, and then the compiler will have a harder time to optimize it. And actually, we have a backup slides here. We found that the first set of columns are the average speed up by applying different lengths of the transformation sequences. And second set of columns is the percentage of loop benefit from a certain length of transformation sequence. And the last one is the average speed up from the benefited loops. And you can see that from sequence length of from 1 to 3, the values are quite stable across different transformation lengths, but at sequence length of 4, we usually don't see benefit. And we believe with a longer sequence than a sequence length of 4, the benefit will get even lower. But we do have a exception for clan at higher sequence numbers. Yeah.
I'll take a question from Slido, which is, based on the findings, what would you recommend for those who want to improve compiler stability?
So the main purpose of our work is to raise the awareness of this compiler stability issues, because we believe a less stable compiler is a less effective tool for optimization. So in this study, the purpose is not to use the data to provide advice for the community. However, we did have several heuristics that we found during the study that I think I have already talked about during my presentation. So, yeah.
So, yeah, headroom is defined as baseline upon the minimum of all the mutations, right?
Excuse me?
Yeah, headroom is defined as baseline's performance upon minimum of the mutations, right?
Yes, the headroom also includes, so if all the mutations are slower than the baseline, the headroom is 0. So,
yeah, don't you think it should be the maximum upon the minimum? Because that's the worst your compiler performed versus the best it performed, so.
Yes, it's the minimum of the execution time, so it's the best.
Yeah, but like above the division, it should be maximum of all the mutations, right?
It's the maximum performance, right? Then that's the minimum execution time. So I might not be getting
We can discuss this later. Okay.
Sorry about that.
Okay, I understood.
Yeah.
We're over time, but we'll ask one more question.
Hey, I enjoyed the talk. So your metric of stability, when it applies to ICC, GCC, and Clang, seems to be inversely correlated with their reputation for good performance.
Yes.
So it's almost like a fighter jet, which is really unstable but fast, versus a commuter, which is stable but not fast. Do you think you have to choose stability or performance, or can you have both?
So what we found is ICC is the most sophisticated one among the 3 compilers, and it usually produces the fastest code for the baseline. However, because it's more aggressive optimization and likely more brittle optimization process, it's more prone to instability to other compilers. Then the question is, when the programmers actually use the compilers, are they always going to supply the compilers the best structured code? Because when the compiler developers develop their compilers, they're usually optimize their compilers towards those well-known loop patterns, or those loops are in the popular benchmarks such as spec. These loops are already written in a good way. We are expected it to do so. Then if we only look at their performance results against these loops, it could be misleading if we don't look at the stability results. And in real world, if the programmers write subpar source code with unstable compilers, the seemingly better compiler can actually produce worse code than the other compilers. So that's what we concluded.